All right, it's day 3 of Unit 1. This is Mr. PL's with Calculus, and we are going to be once again finding ways to find limits using various different strategies. We're going to be using substitution, graphing, and simplifying. All right, so as we jump right into it, so we have on our first question, kind of similar to what we did on that last video. I'm going to factor out x because I see both of these terms both have an x. So once I factor that out, then I can see that I'm left with x squared minus 9, which can be factored out using differences of squares, because this is essentially the same thing as x plus 3 times x minus 3. If you use FOIL on this, you will get this exact same answer. And then once you've done that, then you can cross out x minus 3 on both top and bottom. Once again, still keeping it in limit notation. And then once I got here, then I can just plug 3 in for x and solve, because essentially I've gotten rid of the whole, which means I've gotten rid of that indeterminate solution, that 0 over 0, which is causing me to not get a real answer. So now I'm getting a real solution, which happens to be 18. So 18 is the limit at 3 for this function. So that means that's the height of this function at 3. Now, we're also going to be solving questions using what's called conjugates. And now, the algebra gets a little bit tougher when you see a question like this. This is just an example. Now, what you do whenever you see these radical signs on either a numerator or a denominator, what you end up doing is using what's called the conjugate. Think of this as a binomial. Think of this as two terms. This is one term, and then the 4 is another term. And then we have right here a minus sign in between that binomial. Now, a conjugate would be the exact same two terms, but instead of having a minus sign in between, it would have a plus sign in between. So which means that this which I've circled and this which I've circled are conjugates of each other. Meaning they are the exact same two terms, one's plus, one's minus. Now, why does that matter? Because like in differences of squares, whenever you multiply two things that have one plus and one minus, when you do FOIL, the outers and inners will cancel each other out. And that's essentially the reason why this is going to end up working. Now, of course, if you multiply the top by the conjugate, you have to also multiply the bottom by conjugate. Now, in this kind of question, it does not help to distribute. It does not help to multiply x minus 9 times the first term and times the second term. It does not help to do any of that, or to do a FOIL process, actually, is what would have to happen. This times this times this. I wouldn't do any of that because what's going to end up happening is it's going to cancel out with the whole anyway. So I'm not going to do anything on the bottom. I'm just going to leave the bottom the way it is. So when I multiply this times this, well, x plus 7 times x plus 7, if they're both square root, anything times itself is squared, and squared is the inverse of square root. So essentially, when I go back to pen here, if I multiply this term times this term, I get just x plus 7, which is here. If I multiply negative 4 times positive 4, I get negative 16, which is this term here. Now, if you're keeping track of the FOIL process, I've done the first, I've done the last. Now, the reason why I'm not going to do the outers and inners is because the outers and inners are going to cancel each other out. So the outers, which will be these two terms, and the inners are these two terms, they are going to be exact opposites of each other. And therefore, when you add them together, they're gone. And that's the whole reason why we're using this as a strategy. So I'm left with this. Now, this can actually be simplified because I could then change x plus 7, minus 16. I'm sorry, the parentheses don't even need to be there. It's not squared. It's not protected by the parentheses, so 7 minus 16 is just negative 9. And therefore, these two will cancel each other out, which is perfect because now we're left with just this. All I have to do at this point is plug 9 in for x and solve, which it looks like the answer is going to be 1/8. If I put 9 in for x, the limit ends up being 1/8. All right, so here's another example of the exact same question. This is a conjugate question as well. And I know that because I have these square roots, they have binomials, and I know there's going to be either a plus or a minus in between. Now, if this is a minus, then the conjugate would be a plus. And whatever you multiply the top by, you have to do the same to the bottom. So it's also t times all of this. All of this is like in parentheses. Now, you can see over here, that's basically what I've done. This times this, so this times this would be t plus 2. And square root of 2 times square root of 2, well, once again, square root of 2 squared, square root and squareds cancel each other out. They're inverses of each other, so we're just left with negative 2. The plus 2 and the minus 2 are going to cancel each other out. That's why I crossed them off here. And then we just have a t on top and bottom. A t times 1, I guess, essentially on top, is just t by itself. a t by itself in the product down here. So therefore they can get canceled out, and I'm left with just this. And once I've gotten to this point, I have now simplified. I've gotten rid of that indeterminate solution. So therefore, if I plug 0 in for t, I should get a real solution now. And that's where I end up getting square root of 2 over 4, or 1/4 root 2. Same answer. Of course, anything equivalent to that would be acceptable. All right, another conjugate question, but this time it's on the bottom. Sometimes the conjugate will be on the top, sometimes it will be on the bottom. Since I'm at it, I might as well factor this while I'm at it. This is a perfect binomial, differences of squares. And down here on the bottom, actually, let's keep it going forward. So then I'm going to multiply both top and bottom by root x plus 3. Root x plus 3 would be the conjugate of that bottom. Root x minus 3. After taking a second look at it, yeah, there's actually two ways to do this question. You could multiply the top and bottom both by the conjugate of the denominator, and that would end up working out. But actually, there's a weirder little trick here that we can also do. This x plus 9 cannot be touched, okay? But if it's a minus, because all differences of squares have to be minus, what we can do is we can do the square root of this, square root of this, and this is just a different way, and actually it's going to be less work than what I was describing a second ago. Square root of x is square root of x, so that becomes the first term. So once again, we're factoring something that you wouldn't normally think is a perfect square, but that's okay. The 9 is a perfect square, thankfully, so that's just going to be 3. So this times this is this. This is really the exact same thing. This is basically differences of squares, and I'm factoring even though the square root of x is just square root of x, which is over here. Then I can cross this off with this because those happen to be the exact same thing, and I'm left with just these two terms. And once I've done that, then I've gotten rid of that hole, and I've gotten rid of that hole, I've gotten rid of that indeterminate solution. Therefore, I plug 9 in and I solve, just as normal. So sometimes there's going to be more than one way to solve these questions, and once you've done enough practice, you just kind of get used to finding like the shortest method of doing it. But honestly, it doesn't really matter. In this case, I'm doing exactly what I was about to suggest in the last question. I'm literally just going to use the conjugate of the top. The conjugate of the top is going to be the exact same binomial. The only difference is the fact that it's, instead of minus, it's going to be plus. And you have to multiply both top and bottom by the exact same thing. Now, once again, don't do anything on the bottom. Just leave the bottom alone. And hopefully, if everything works out, because usually it does with these questions, then that is going to end up being, it's going to disappear with the whole anyway. So this times this, square root of x times square root of x was just x. Square root of 5 times square root of 5 is just 5. And of course, since it's a negative times a positive, of course, it's going to stay a negative. So that gets rid of these. So now we're left with just 1 over root x plus root 5. And then I can plug in my 5. I can just substitute it in and solve. And there's my answer, 1 over 2 times root 5. All right, example number 4. So this time we have a complex fraction. These questions get a little bit more difficult. So in this question, I have a denominator of x and a denominator of 2. So what I'm going to do in this case is I'm going to multiply both pieces by the other denominator. I'm going to multiply this piece by x over x. I'm going to multiply this piece by 2 over 2. So once I do that, I'm going to get 2 over 2x. And over here, I'm going to get x over 2x. And of course, once the denominators are the same, then you can, of course, subtract them. So it's 2 minus x. So it gets 2 minus x. Because once you multiply this times this, you're going to get 2x both on both denominators. And that's where it gets me to here. Now, there's a couple of different ways you could do this. And as you can see, I've chosen one way. You could multiply both by 1 over x minus 2. That would be one way of doing it. But you know what? This is division. I'm going to take this entire thing and I'm going to do what I call leave, change, change. I'm going to leave the top alone. I'm going to change this to multiplication. And I'm going to change the bottom fraction into what we call the reciprocal, which means you're literally just taking it and you're flipping it to 1 over x minus 2. Now, what you see when I do that is that if you factor out negative 1 over here, we end up getting the exact same factor here and here. So therefore, we can cross those off. Simplifies down here just by multiplying across. And then once I've done that, because I've eliminated that hole, then essentially I can just plug 2 in and get my answer. All right, last example. Once again, another complex fraction question. I'm going to do the exact same thing. I'm going to multiply both of these pieces by the other denominator. So I'm multiplying this side of the complex fraction on top. by x minus 4 over x minus 4. I'm not going to multiply this piece by 3 over 3, because anytime you multiply something by a number over itself, you're essentially multiplying it by 1. You're not changing the value at all. Now, I'm going to have to use distributive property. This times this times this. I get 6x plus 9. And then I cross multiply. Oh, before I do that, sorry, I got the same denominator for both. 3 times x minus 4 is 3x minus 12. And then once I've done that, I've multiplied both denominators, I can add the two numerators. So I added this plus this into this. All right, didn't do anything on the bottom. The bottom of the complex fraction stayed the same. I'm just putting it over 1 because I'm going to use leave, change, change. I'm going to move the bottom by flipping it to the reciprocal. Now, once again, this could be both. It has a common factor of 11. So I factored out that common factor. And then perfectly, I got x minus 1 can be reduced out. Multiply across. Substitute your 1 in because you've now gotten rid of the whole. And there's your answer. You found your limit. You've gotten rid of the whole so that you can now just plug 1 in for your answer. Now, of course, if I go back here, my first instinct, and I probably should have mentioned this at the very beginning of the video, is just to plug 1 in for x and see if I get an answer. Because if that works, if I can just plug 1 in, I'm going to do that because that's going to be the easiest method to this question. I knew right away this is an indeterminate solution because 1, if I plug it into the denominator, 1 minus 1 is 0, and you can never divide by 0. Which then I knew I needed another strategy. And this happens to be, pretty complex strategy, but it is a strategy nonetheless in order to find the limit to the solution. Thanks again for watching, and I'll see you again in the next video.